Hey, good afternoon. Today, hopefully, I'll get to finish um, the multi-threaded kernel slide set, and then we'll start talking about uniprocessor scheduling. So let's finish this up. We talked about implementing mutex. We also talked about implementing semaphores. So the last thing to talk about is implementation of condition variables. So it's very similar to the two previous implementations. Um, we're going to have a private element, which is this queue of waiting threads, and we're going to implement three functions: wait signal and broadcast. Now the wait signal is going to get a mutex. It's it adds the running thread to the waiting list. It then calls onto the scheduler's suspend function. It passes the mutex inside the suspend. We're going to release the mutex, and we're going to put this guy to sleep. As you can see, when we come back, the first thing we're going to do is to lock the mutex. So this should be kind of what we have been saying. So if you remember in the previous in concurrency lectures, I kept telling you that inside wait, what's going to happen. So this is the implementation of what's going to happen. So essentially the elements here are adding the TCB, adding the thread to the waiting list, suspending it, and once we come back out of suspension, we're going to lock the mutex again. Now let's look at signal. Signal is going to look at the waiting list, and if it is not empty, then it's going to remove a thread from the waiting list. Now here, this remove doesn't necessarily need to be a FCFS. So you probably have some implementation of remove. There might be some, some policy on who to wake up, but just let's put everything under the umbrella of remove function. So this is going to choose one TCB or one thread from the waiting list. And then we're going to just call onto the scheduler to make this thread ready. And finally, broadcast is going to remove everybody and put them in the ready list. Now, there is one difference if you stare at this code a little bit. You notice a slight difference between this one and mutex and semaphore. In particular, you don't see any notion of locking. There is, if you remember, with semaphore, we had semaphore spin lock. With mutex, we had mutex spin lock. But here, there is no spin lock. There is no variable to be used for mutual exclusion. Whenever we want to, change the state of CV. And you might ask why. Is there anything wrong with this code? Do I need to, maybe add a spin lock at the beginning, lock the spin lock, and at the end, for all these functions, add spin lock.lock and spin lock.unlock at the beginning and end of them. Now, the answer to that question is no. You don't really need a spin lock. The reason for that is we have this convention that requires programmers to call these functions only if they have already locked a mutex that is associated with this CV. So as a reminder, we had monitors which included a single mutex and 0 or more CVs. So if you are holding the mutex and then you're calling wait, signal, or broadcast, we already have mutual exclusion. So when wait, signal, and broadcast are called, we're sure that no other thread is going to call them, because the one who is calling already has locked the mutex. So that's why, if you remember in the concurrency lectures, I was telling you that never call these functions without holding the lock, without locking the mutex. And you can see now, because this is the implementation. So the implementation assumes that you have done that. So if you go against that convention and do what is called naked signaling or naked broadcasting or naked wait, you're going to cause problems. Okay. Now we saw the implementation. Let's just, for practice, try to implement condition variables using semaphores, because semaphores are as powerful as mutexes, and they can actually provide scheduling constraints. So just as practice, let's try to implement condition variables using semaphores. So the first take you might think of, the naive implementation would be for wait, for us to just unlock the mutex, then call P with the semaphore that you might have in your implementation. And once you come back, you lock the mutex again. And then for signal, you just call V. Now, what's the problem with this implementation? So this implementation is not going to work. The reason is signal in condition variables should not have memory, meaning that if you call signal 10 times without any thread waiting, the next thread that calls wait has to wait. So all those signals should get wasted, and the new thread that calls wait has to wait. It shouldn't say that, oh, in the past signal was called 10 times, so next 10 waits should not wait. So that is not the case. However, if with this implementation, semaphore.v has memory, because it's going to increase the value of the semaphore. So if you call this signal with this implementation, then you're going to have a problem, because then after 10 signals, if somebody calls wait, they're not going to wait. They're going to go, because the V has increased the value of the semaphore, and P is going to go. There is one more problem with this implementation. We'll talk about it in the next slide. So let's first fix this one. Let's try to fix the memory problem, memory-less problem. So this implementation has memory. It has another problem as well, but let's first focus on the memory. Let's try to have another implementation that doesn't have memory. So probably we want to here check something before calling V. So maybe what we want to do is kind of check and see if semaphore's queue is non-empty, meaning that somebody has called P, then call V. Otherwise, don't call V. Now, this implementation, conceptually, this signal doesn't have memory, conceptually, but practically it's not going to work. The reason is there is no way for us to have any access to the semaphore's internal variables. The only two operations that are defined on a semaphore are P and V. So there is no way for us to look inside the semaphore. So this is not going to work. Now, the other problem with this, which was a problem with the first take as well, is with the wait function. Now, what is happening here is that this wait function is not atomic, meaning that it's not going to atomically unlock the mutex and then put itself to sleep, because there are two operations here happening. One is the mutex being unlocked, and then P is going to be called. Now, each one of these two are atomic by themselves. We know that P is atomic. We know that unlock is atomic. But if you have these two operations sequentially, you could get interrupted in between, and that would be against having the wait function atomic. Okay, so this is not going to work because, again, this wait function is not atomic. And you can compare this with the implementation that we had. Let me actually go up and show you that in this implementation, wait is atomic. The reason for that is that we're going to call this suspend function to do all of that. And the way we implemented this suspend function, we made sure that it is implemented atomically. So this suspend is going to release the mutex and put the thread to sleep atomically, and it's not going to be interrupted in between. So this implementation was atomic from when you release the lock until you call onto the until you put the thread to sleep. But this take one and the same take two, because we didn't change the wait, this implementation is not atomic. Okay, so now we have two problems that take one and take two haven't addressed. The first problem is with the signal, because we have memory. The second problem we have is with the wait, which is not atomic. So how can we solve these two problems? The idea here is to have separate semaphores for each waiting thread and put these semaphores in a queue. This is very similar to the solution we came up with readers writers problem or lock. The last one, if you remember, we created the last solution to not allow writers to starve was to have this queue of CVs and have each writer to have its own CV and then put all these CVs into a queue. So let's do that. Okay, so I'm still not addressing the yeah, I'm still not addressing the second problem, which was the atomicity. Let me actually check something before I move on. Yeah, so let's first address this memory issue, and then I'll probably leave this one to solve this one to you. But let's focus on fixing the signal. So we're going to make everybody, so each thread, to have its own semaphore. Now, when you call wait, we're going to create a new semaphore for you, and then we're going to have this queue we added to hold the semaphores. So I'm now adding this semaphore that I created to my queue. Then I unlock the mutex and I call on this semaphore.p. And then when I come back, I unlock the mutex. Sorry, I try to lock the mutex again. And let's look at signal. What does signal do? Now, signal can look at this queue and see if this queue is empty or not, because this queue we added. It's not the internal queue of a semaphore. We added this queue, and we can check if this queue is empty or not. Now, if this queue is not empty, then we remove from it and then we signal. So we send V to the specific semaphore that we get out, and that's it. Now let's talk about, so this actually solves the memorylessness because now I'm able to check this queue and see if it is not empty, then I send V, otherwise I don't do anything. So this solves the memorylessness problem. What about atomically putting someone to sleep and then unlocking the queue? This implementation actually has that as well. The reason is we add this this thread to, so if a thread calls wait, we add it to the queue while we are holding the lock. So we create a semaphore for this new thread that called wait, and we add it to the queue, and then we call unlock. So we have created this mutual exclusion. So when you're added, you're holding the lock, then you unlock and you call P. Now, the problem we had previously in the previous take was we were doing just this mutex dot unlock, then semaphore dot P. And the problem was right after we unlock the mutex and before we call P, we could have gotten interrupted. And maybe a signaler would signal, right? And then we would call P, and that would be bad. Now, with this implementation, with this new implementation, it's fine if we get interrupted here because we have already added ourselves to the queue. So here, a signaler would see us. A signaler would see that we are in the queue, and then they would call V on our semaphore, which is good because when we wake up and we call P, now everything works the way it should have worked. Because if I called wait first, and then somebody called signal, I should now go, and this happens because the signal was sent to my semaphore and I go. Again, I repeat, the problem that we have with this one, let's actually analyze this and see why this is a problem in regard to this not being atomic. Let's say I release the mutex here, and before I call P, I get interrupted. So I get interrupted here. I want to put myself to sleep. I get interrupted. Now, a signaler can now go, and then the signaler would check this queue, and nobody is in the queue. Let's assume that this can happen, and we can check the queue because I still haven't called P, right? I still have not called P, so I'm not in the semaphore's queue. So this signaler would look at this queue. I mean, again, assuming that this implementation can be implemented, and I'm not there, so it doesn't send a V. And then let's say I wake up, and now I go to sleep because I'm going to call P. And this is bad, right? Because I called V, I called wait before somebody calls signal, so I should receive that signal. But because I got interrupted, I basically missed that signal. Now this has been fixed in this implementation because I first add myself to this queue, and then I unlock the mutex. Now the signaler will definitely see me here and will send a signal, it will send a V to my semaphore. And this is good because when I wake up, then I can just receive that V when I call my P. Okay. So in summary, we in this lecture, we talked about implementing basically threads. We talked about user-managed threads versus kernel-managed threads. We talked about implementations of mutex, semaphore, and condition variables. And we did so using disabling interrupts, enabling interrupts, using test and set. What I didn't talk about was how you could actually implement mutex or semaphores or condition variables using other read, modify, save operations like swap or test and swap. So you could indeed use those to implement the same concepts, which usually is asked during the exams. Okay, now I guess I can answer some of the questions you guys have asked. Okay, what do you mean semaphore's queue? I thought semaphore only had a value. Right, so by semaphore queue, I mean this queue that we talked about, implementation of semaphore. If you remember, in the implementation of semaphore, we had this waiting queue for the semaphore. So I was talking about this queue of the semaphore. So a semaphore internally has a value, right? So this is the value of the semaphore, but also a queue of those who are waiting. So in the implementation of condition variables, I said, let's assume that we have access to this waiting queue, then that was the take two. So that's what I was talking about. Okay, that was a good question. Now, the second question I have is, in the CV implementation, why do we not unlock the mutex in wait? Never mind, I misread. Oh, okay. Are semaphores allocated from heap? If so, would we ever encounter memory issues from allocating semaphores for each waiting thread? I assume that you're asking about this implementation. So implementation of condition variables with this. So yeah, in this implementation, let me clean it up. In this implementation, yes, we're allocating these semaphores. We're allocating these semaphores dynamically. We're using new to allocate them. So yes, now this, of course, you could end up having issues with memory allocation. So this is just an idea of how to implement. But if you really want to implement this for, you know, a system library or something, then of course your wait function should cover all the things that could go wrong and raise issues appropriately. Okay. Does the last approach thereby enforce that whoever was the first to go to sleep becomes the first to definitely wake up? Not necessarily, because again, I have this remove function here, and I'm not talking about how we are removing, right? So this remove could have any sort of policy you want. Maybe you want to remove threads from this queue based on their priorities. Maybe you want to remove based on other factors, right? So whatever this queue implements then would be what you have. Usually in systems, you probably want to have different. So I believe what libraries usually provide is a guarantee that you will eventually wake up. If this queue is getting a lot of signals, then you will eventually wake up, but they don't provide any guarantee about the order at which you're going to wake up. Of course, you can implement something that makes sure that it's first come, first serve. So that's possible. But when, as a programmer, when you're using these, you shouldn't make any assumption about the order. Also, what type of data is in the semaphore's waiting queue? It's probably just TCB, right? We have a queue of TCBs because we want to account for all the threads that are waiting. Does queue by definition have FIFO property though? So the first thing that went into the queue would be removed first. But I guess I explained, right? So these don't count them as FIFO queues. They could be any sort of queue. They might have you know, some sorting going on. When you add something, that it could be a binary queue and it just sorts them. When you insert something, yeah, I mean, I'm not making any assumptions. I'm looking at this queue as a medium to store TCBs, and then there is a remove function for it to give me a TCB, and that's all I need. Now, you know, different implementations could have different types of queues and different types of removes and different types of policies and all of that. So we don't care about them here. All we need is to just get somebody and send it a signal. If you care about, then you can have your FIFO queue, for example. Okay. Good questions. Okay, so we're done with this one. Now let's move on to next lecture or next topic. Maybe that's a better term. So we're now starting the uniprocessor scheduling. So I'm not gonna promise, but if I get a chance, I may talk just tiny bit about multiprocessor scheduling. It will depend on how fast I can finish uniprocessor scheduling. But if I get a chance, I'll talk a little bit at least about multiprocessor scheduling, or at least I should talk a little bit about Linux schedulers. So we'll see if I have time. If I don't, then we'll just focus on uniprocessor scheduling. Okay, so a little bit of history. So this is from Linus Torvalds. I'm not sure if I'm pronouncing his name right, but this guy is the guy behind Linux, the one who invented Linux. So by year, this is a quote from him in year 2000. He said that basically, you know, a scheduling problem is solved, and now scheduling is easy because the problem is solved. So verbatim, he says, and you have to realize that there are not very many things that have aged as well as the scheduler, which is just another proof that scheduling is easy. Then, so this is, oh, actually 2001. So if you remember from the first lecture, around 2004, we started to see the rise of multi-processors. And when multiprocessors started to come, then people, you know, started rethinking about scheduling. So scheduling was fine for uniprocessors, which is the topic that we're gonna focus. But when multiprocessors came in, people started to looking at it again. And there is another quote from Linus that says, okay, right now we have we have multiprocessors, so it's not as easy as it was with uniprocessors, but it still is quite solved. So don't worry. All we need to do is to do load balancing between our between our processors. That's all we need to do. So don't panic. It's still an easy problem. There is a paper that I have here. So if you're interested, this is an easy read. I absolutely encourage you to take a look at this paper. So it says, so the title of the paper is "The Linux Scheduler: A Decade of Wasted Cores." So this is in 2016 when this paper was published, and they showed that, you know, this problem that we thought is very easy and we shouldn't panic and it's like solved and stuff, and we have a good implementation of it, in some cases leads to 138 times a slowdown in our threads, in execution time of our threads. So highly inefficient, in fact, highly non-optimal. And unfortunately, in SE350, I don't get a chance to talk about why. So we will just focus on this problem that was solved. So we're going to focus on the uniprocessor scheduling and talk about, I think I have 8 or 9 different scheduling policies, and then we'll look at the trade-offs. But really, this is just the beginning of thinking about multiprocessors. And, you know, we didn't actually solve this problem of multiprocessor scheduling completely before we were hit with another issue, which was heterogeneity and new types of systems with not just, you know, CPUs, but also GPUs and TPUs and you know, FPGAs and all sorts of other processing elements. And you know, when we get to the end of this course, so at the end of the term, I will post a video, and I will probably somehow force you to watch it. It's from 2000 and it's from last year. It's a keynote talk from a very well-respected top-tier conference in operating systems, and the message is we have a problem, and that problem is that we're focusing or we're relying on Linux too much, and Linux is not solving our problems. We need new designs in this era of new hardware coming out every day. We need to rethink operating systems, and the scheduling is one of those problems. This is one of my actual interests. I do work on this. So any of you who are interested in, you know, scheduling in distributed systems, scheduling in data centers, scheduling in even, you know, operating systems. So this is a topic that is of my interest. So if you're also interested in you know, any topics related to distributed systems or operating systems in terms of scheduling and resource management, reach out to me and we can talk about, you know, research opportunities that might exist in my group. So without, you know, any further in discussion, let's get into it. So I'm going to define some terms, and then we're going to be using these. So from now on, do not pick on me if I use tasks, threads, processes, jobs. I'm going to use any of these to mean a unit of execution. So if you have a system that the unit of execution is process, then we're talking about process. If you have a system that the unit of scheduling is threads, so we're going to talk about threads. If you're talking about, you know, the RTX that you have, the unit of execution is tasks, so we're kind of talking about tasks. So I'm going to use these terms interchangeably, and all I mean is a unit of execution, what we want to schedule. Now, the other thing that is important to define is a workload. so whenever you hear me talking about workload, all I mean is a set of tasks, is a fixed set of tasks that we're talking. A scheduling algorithm is basically an algorithm that decides which task to run first, or basically putting an order on the execution of tasks. The overhead of a scheduling is basically any extra work that we have to do in order to schedule tasks. So, you know, every time we're running the tasks, we're not paying any cost. Anytime we are not running tasks, either we're making a decision on which task to run or we're context switching between tasks. That's the overhead of our scheduling policy. We'll see it. We'll discuss that in further details. Preemptive schedulers are schedulers that can preempt tasks, basically stopping a task and potentially context switching between tasks. Work conserving schedulers are scheduling policies where if a CPU is available and if a task is ready, then the CPU will be the task will be scheduled on the CPU. So CPU is always utilized if we have tasks to run. So that's the definition of work conserving. Now, a non-work conserving scheduler would possibly leave the CPU idle even if you have tasks in your systems in your system waiting. Now, one thing to note here is that non-preemptive schedulers, for non-preemptive schedulers that cannot preempt tasks, then being work conserving is not always a good idea. So you could think of, for example, if you have a system where you have, bunch of very low priority tasks, but these tasks are very long, and then you have these frequent high priority tasks that come, and let's say you know when they come. Let's say it has a fixed frequency, and you know when it's gonna come. Now, let's say your CPU becomes ready, and you have 10, low priority tasks, but you know that a high priority task is gonna come in, let's say, 2 microseconds. But the execution time of all these low priority tasks are more than 2 microseconds. Maybe they're like 5 microseconds. All of them are more than 5 microseconds. So it might be a good idea for you to not run any of them and just wait for 2 microseconds to get your high priority task and be able to run that high priority task. And after that, you can then go and run your low priority tasks. So, if you want work conserving a scheduler, then you have to start running one of those low priority tasks. But if you cannot preempt them, then there is a probability or possibility that your high priority task comes, and then it has to wait for these very low priority tasks. And that might not be something that you want for your system. Okay. So lastly, in what comes next, we're going to be focusing on preemptive schedulers and work conserving schedulers. So we're not going to look at non-preemptive and non-work conserving schedulers. We're going to focus on these two unless otherwise stated. So that's that. Now we're going to focus on scheduling tasks here in this ready queue. So that's basically the CPU scheduler's job to pick the next TCB or the next thread or the next task or the next process, you name it, whatever is the unit, to run on CPU. But whatever we're going to talk, all the policies that we talk, you can use them elsewhere. You can use these policies, for example, to manage I/O, because you might have I/O requests and you might want to schedule I/O requests. You can use most of the policies that we talk about there. You could use these, for example, in your mutex queue, right? We talked about mutex having a queue of tasks, or semaphore having a queue of tasks, or condition variable having a queue of tasks. And you could implement any of the things that we talk about here, not all of them, but some of them, in those queues as well. So we're going to just talk about scheduling policy. We will focus on this queue, but most of the things that we say are applicable in other queues that you might have in your operating systems. Okay, now to set the stage for what is going to come next, let's talk about what kind of execution model we're going to consider. So we're going to consider our tasks or threads to have this pattern of doing some computation. So doing some loads, stores, multiplication, add, like all sorts of things. So these are this is what we're going to call as a CPU burst. So these are instructions that are going to be executed on the CPU. And at some point, at the end of your CPU burst, comes an I/O request. So you're going to ask for a file, you're going to ask for a socket, you're going to, maybe lock a mutex or something, and then you're going to go for an I/O wait. So you're going to be waiting for I/O. Now we're going to call it an I/O burst. You can call it whatever you want, but this is a time where you don't need CPU. You're, either you're waiting for I/O for your I/O request to finish, or maybe you're waiting for a mutex to be released, or whatever reason that you don't need CPU anymore. And at some point, whatever you're waiting for is done, and then you come back, and then you will have another CPU burst. So then you start again using the CPU or needing the CPU until again something happens and you don't need the CPU anymore. So that's what we're going to focus on. So we're going to think about this. Now, in the simplest condition, you might have a task or a thread that has only one CPU burst and then it ends. So it may not ever go to I/O. It might just do some computation and then die. So that's the simplest model, where you have a single burst and you're going to be done. But in more complicated scenarios, you might, again, have this, this repeated CPU bursts, and then waiting for I/O, and then CPU bursts, and then waiting. If you look at the frequency of certain CPU bursts, it's usually the case that most of the tasks, most of the threads, most of the jobs, most of the tasks in our system have very short CPU bursts. So whatever solution we come up with should kind of take care of the majority of our CPU bursts. So we want our scheduling policy to be friendly towards short tasks, and we'll see how this plays a role. So in this figure, if I to explain it again, on the y-axis I have the frequency, and on the x-axis I have the burst duration, so how long each CPU burst takes. And as usually, if you study your systems, you're going to have such a graph where the peak of the majority of your CPU bursts are going to be short. And usually, sometimes you have something like this, where you have a very small fraction of your CPU bursts are very, very long, and you want to probably somehow prioritize these short ones because you have a lot of them. Okay. Now we're going to assume that, unless otherwise stated, we're going to assume that, so I should have changed this. This is going to be a process per process. process. So we're going to assume that each user has a single process and each process has a single thread, and different processes are independent. These are very restrictive assumptions, but once we know how to deal with this, then we can, relax some of these assumptions and think about other issues. So for instance, it's important to talk about fairness when we talk about it, to know, are we going to enforce fairness across users? Are we going to enforce fairness across processes? Or are we going to enforce fairness across threads? So with these assumptions, all of them are equal. So there is only a single thread per process per user. But in general, that might not be the case. You might have a user with multiple processes, and each process might have multiple threads. Then if you're talking about fairness, it's important to say which level you're talking about. Are you being just fair among all threads? Are you going to be fair among all processes? Or are you going to be fair among all users, right? And you can see that each one of these has its own importance. So for example, if you're a data center manager and you have users, you don't really care about how many processes or threads they have. You want to be fair among users. If you're, doing an operating system design, usually the system is being used by a single user. Again, for example, for your laptop or for your tablet or for your cell phone, there is a single user at any given time using the system. So you don't need to care about users. You can care about processes, for example. So if you're now writing a scheduler for a, let's say, user-managed multi-threading, then you probably want to be just fair among threads. So again, we're not going to go to the details of these, but they become important in different systems. For these lectures, we're going to assume that there is just a one-to-one-to-one relationship. Now, what are the metrics that we're interested in? So the first metric that we're interested in is performance. Now, there are two main sub-metrics in the performance metric. The first is response time. Now, what is response time for threads? The response time is from when a thread becomes ready until it finishes. So that's basically a response time. So from when it comes until it gets out. So that's a response time. Now we can have an average response time, so average over all threads. So how long were they in the system? Because response time is basically how long a task is in the system, either waiting in the system to be scheduled, or it's already scheduled and it's running now. So how long that the total time takes is the response time of the thread. And if you have a bunch of them, then you can just take average over all threads, and that is a metric that we're interested. Basically, average response time. The shorter that is, the better, right? So the shorter threads stay in the system, the better, because then you're more responsive. Because the responsiveness of your system is when a task is issued until it's done from the user's perspective. So you want to minimize this. The second thing that might be important for your system is throughput. And you usually want to maximize throughput. And what is it? What is throughput? Throughput is basically how many tasks you finished in a given time period. So the number of tasks that you finished divided by the duration of time. Now, these two metrics are not dependent. So you could improve average response time and hurt throughput. You can improve throughput, basically maximize throughput, and hurt average response time, meaning that, you know, make it worse, increase average response time. You could improve average response time and also improve throughput. You could hurt response time and hurt throughput. So there is no relation, no correlation between response time and throughput. So these are two independent metrics. So improving one of them may or may not affect the other one. Now, we'll actually see examples of this. I may not point to it that, okay, look, this is an example where throughput hasn't changed, but response time has been improved, right? Or look, this case, we are improving throughput, but response time is hurting. I mean, I'll try to point to them, but it will come in the future slides. So we have all sorts of cases where we're, you know, playing with these, and one of them gets better, one of them gets worse, or both of them get better, or both of them. I mean, hopefully both of them don't get worse, because that's bad. We want at least one of them to get better. But anyhow, they're completely independent. So fairness is basically, in the context of a scheduling, is usually defined on how much time each task gets on the CPU. And we kind of want this to be equitable. Now, what is equitable? So what is the underlying definition of equal treatment of tasks? That's a philosophical question. In the most naive way of defining it is probably we want to, let's say, measure time on CPU and say they have to be equal. But that not necessarily needs to be the case, right? Maybe I have a task that needs a lot of I/O, and it has really long I/O bursts and very short CPU bursts. So this task doesn't need CPU by much. And if I enforce equal CPU time between this task and another task that actually doesn't need I/O and only needs CPU, then maybe I'm unfair to both of them, right? So there are different definitions of fairness. In fact, my PhD thesis was on this issue, defining fairness and enforcing fairness in data center schedulers and multiprocessors. But that's we're not going to go there, of course. So we're going to just talk about this naive way of defining it, which is equal CPU time, and we're going to leave the rest to, you know, to future. If you're interested, you can actually study it. Okay, and I guess I talked about, you know, what do we want to be fair about? Do we want to enforce fairness across users? Do we want to, you know, be fair across processes, threads, and so on and so forth? One thing that we can say, and usually is true, is this last one, which we will actually see in the future slides. So usually fairness and performance usually are not aligned. So if you really want good performance, meaning if you want to minimize, for example, average response time, usually it comes with a cost of fairness. You're gonna be unfair to certain tasks. And if you want to be fair, usually it comes with a cost of performance, meaning that if you want to be fair, then your performance will suffer. So we'll see this as we go. So usually there is a trade-off between performance and fairness. The first scheduling policy that we're going to talk about is first come, first serve. Now that I have, you know, laid out all the intro, for this. Let's start with the first out of 8, I think, if I'm not mistaken. We have 8 scheduling policies. The first one, the simplest one, first come, first serve. The name suggests what it means. Now, one thing I have to note is if you have tasks with CPU burst, then IO burst, and then CPU burst, and then IO burst, every time they go for IO, they're out of the system. So when they come back, they're going to go to the back of the list in first come, first serve. So, you know, a task comes in, it waits until its turn, then it starts running. Then once it finishes and it wants to go for an IO, then it goes for an IO, and then when it comes back, it's going to go to the back of the list, back of the queue. So it's like always first come, first serve, and whoever goes for IO and comes back, it's going to go to the back of the list. Now, let's look at a simple example. Let's say I have 3 threads, and let's assume that these are simple threads with only single CPU burst, and then they terminate. So the simplest case, so T1, T2, T3, and each one of them has CPU bursts in whatever unit of time you want. Let's say microsecond for the sake of argument. So T1 has a CPU burst of 24 microsecond, T2 3, and T3 3. Now let's suppose that they have come to the system with order of T1, T2, and T3. Then FCFS leads to this scheduling outcome. So T1 first will be scheduled because it arrived first, then T2, and then T3. Now let's look at the performance metrics in this case. So what is the wait time of T1? So assuming that all 3 of them came at time 0, then T1 waited for 24 units of time, let's say microseconds. T2 waited for 27 microseconds because it came at 0 and it finished at 27. So that's 27 units of time. And T3 waited or was in the system for 30 time units. So average wait time is going to be 0 plus 24 plus 27 divided by 3, which is 17. Now, excuse me, this is average wait time. So T1 did not wait. It came at 0, it started running immediately. T2 came 0, it started running at time 24, so it waited for 24 units, and T3 waited for 27 units. So this is average wait time, and average response time is basically 24 plus 27 plus 30 divided by 3. So now let's look at another possibility. Let's assume this time that T2 was first, then T3, and then T1. So let's assume that this was the order. In this case, the scheduling would lead to a different outcome. So T2 first will run, and then T3, and then T1. And if you do the calculation, you will see that wait time has decreased from 17 to 3, and response time has decreased from 27 to 13. So now let's pause here and look at throughput. So in this case, in both of these two scheduling policies, if I go back, so in both of them, I have finished 3 tasks at time 30, let's say 30 microseconds. So my throughput is 3 divided by 30, which is 1/10. 1/10 of a task per unit of time. So in both cases, I have the same throughput. But as you can see, response time has dramatically decreased. In fact, it's less than half. So in the first scheduling, it was 27. In the second one, it's 13. So this is one example where throughput hasn't changed, but response time has improved. So that's one example to show you that, you know, these two are not completely related. Now, What are the strengths and weaknesses of FCFS? Well, FCFS is very simple to implement, but the shortcoming or the weakness is basically short tasks are going to get stuck behind long tasks if long tasks come first. So here is an example. So in this case, on the horizon, I have time. And then up here, I show you the tasks that are scheduled. And down here, I have the tasks that are queued. So initially, let's assume that one task, this blue task, is running. Then 2 more tasks come. They get queued in the order that they come. And then we start executing them. Then another task comes. So again, at any given time, if you look here, you'll see the tasks that are waiting. Now let's assume that this task that has come is a very long task. So it's going to take a long time. And let's say while we're executing this guy, new tasks arrive. So as new tasks arrive, they start queuing up because we're still running this really long task. So the result of running this long task shows up here when we accumulate a lot of tasks in the queue. And these might be actually very short tasks. So all of them get penalized by this big task. All of them have to wait for this big task. And this is basically an illustration to show the weakness of FCFS. It's called convoy effect. And the second scheduling policy that we want to talk about is round robin. Now, I have a very cute robin here, which is kind of round, and I love it. So let's put a heart here. Looks so cute. Or maybe 2. So cute. So now we're definitely not talking about this guy. So round robin is a scheduling policy where we divide time into time quanta with a fixed length. For now, let's assume we have a fixed length. And we're going to go around the table and let every task run for the length of the time quantum. If they finish before the time quantum expires, then we go to the next one. If they don't finish, then we just wait for the time quantum to expire, and then we context switch to the next task, and so on and so forth. So time is divided into time quanta. We let each task run during the time quantum, and then we context switch to the next task, and we put this task that just finished to the back of the queue. So we always keep this queue of tasks that haven't finished, and we just go through them and give them a time quantum on the CPU, and then we preempt. We go to the next one. We put the one that hasn't finished to the back of the queue. Now this guarantees that, let's say if you have, if you have n threads in your queue and the length of your time quantum is q, then each task is guaranteed to have a wait time that is less than n-1 times q, right? So you're going to wait for, worst case scenario, you're the last task in the queue, in which case you have to wait for n-1 tasks before you to run for each one of them for maximum time of queue, and then you start running. Now, one thing to note is that in this calculation, I have assumed that the context switching time is 0. Now, this is a big assumption. The context switching time is overhead, because during context switching, from when we preempt a task until the time that we start running the next task, this is the context switching overhead. During this time, we're not running any tasks. We're just context switching. And this is an overhead. Now, unless stated, you should assume that it's 0. But I will talk about this. If it is non-zero, then what happens, right? But for this calculation in particular, we have assumed that it's 0. If it was not 0, then the formula would be n-1 times q plus this delta, which delta is the time for context switching. So you're going to see n-1 context switches and maximum of q running time for each thread, assuming that none of them finishes before the time quantum expires. So it's going to be n-1 times q plus delta, where delta is for the context switching overhead. Let's run an example. So this is a recurring example. So I'm not asking you to memorize this, but just we're going to come back to this example later on. So I have 4 tasks, T1, T2, T3, and T4. Let's assume that that's the order of the tasks in the queue. So T1 is first, T2, T3, and T4. And these are the execution times for each one of them. And again, let's assume that this is a simple case where each task has a single CPU burst and then they finish. So they're not going to go for I/O and come back. So that's the example. That's the setup. Now, this figure is misleading, so please don't be misled. So the fact that I have similar length for these doesn't mean that they're similar. In fact, if you look at this is from 0 to 20, and this is from 20 to 28. So it's just the order that is illustrated in this with these boxes. The length of these boxes are not indicative of how much this task has run. So for that, look at the numbers. Okay, so with that, let's run round robin. So first T1 runs. Let's assume that the length of the time quantum is 20. So it will run for 20, whatever unit of time. Then we context switch to T2, assuming that there is a 0 context switching cost. So I immediately context switch to T2. Now T2 is going to run for 8, and it's going to be done. So at time 28, I'm going to be done with T2, and I'm going to go to T3, and then T4. Then I'll come back to T1. Then T2 is now done, so I go right to T3. Then I go to T4, and T4 in the first run executed 20, so it has only 4 left. So that's where the 4 extra units of time are spent to finish T4. Now T2 and T4 are done, so I have only T1 and T3. So I, go to T1, then go to T3. And at this point, T1 is done, so I continue with T3 and I'm done. Okay, so let's now look at wait time for each one of them. So just pay attention how I calculate wait time. So what is wait time for T1? So T1 at this scheduling overhead, at this scheduling, the first schedule got 0 wait time. Then it was scheduled here. So from 20 to 68, this is a time that T1 was waiting. So 68 minus 20. Then it was scheduled here. So from when it was preempted to when it was scheduled, that's 112 minus 88. So these are the 2 intervals that T1 was waiting. So that's the wait time for T1, which is 72. You can do this for all the other ones. And then you can see the average is 66 1/4. Now let's look at response time. How can we look at the response time? Response time is easy. we can just look at when each task finished, because that's the time that the task was in the system, assuming that all of the tasks were in the system from time 0. So usually in the exam, tasks come at different times and they might have I/O, but in this particular case where they don't have any I/O and they all were in the system, so we just look at when T1 finished. So T1 finished at time 125. So that's the response time of T1. So that's what you see here. T2 finished at time 28. So that's the response time of T2. T3 and T4, and that gives us a response time of 104.5. Okay, so now let's discuss what is good about round robin. Well, it's better now for short tasks because they're not going to get stuck behind long tasks. You know, even if a task that came before me is long, I'm not going to wait for its entire execution. I'm at most going to wait for a time quantum, the length of the time quantum for this until I get to run. And maybe this task, the short tasks are less than the time quantum, and whenever they get to run, they just finish. So they don't get to wait for the entire execution of long tasks, which is a plus. Now, the weakness of round robin is depending on the length of the time quantum, you might end up doing a lot of context switches, right? So if I make the length of the time quantum short, then I'm switching between T1 to T2 to T3, 4, 5, 6, and then come back and do this again and again and again and again. So I might end up context switching a lot, depending on the length of my time quantum. Now, if the overhead of context switching is non-zero, which is the case in any real system, in real systems, you have overhead of context switching. Excuse me, my laptop is not being charged, so give me a. Oh, it is. That's weird. Is it being charged or no? Yeah, okay, it is. So, what was I saying? Right. So if the overhead of context switching is non-zero, then what happens to throughput? So we can now compare FCFS and round robin in terms of throughput. So if I don't do this, remind me to do this comparison. So depending on the length of the time quantum, we might do a lot of context switching with round robin. So let's say we have 4 simple tasks. So in FCFS, we're going to just do 3 context switches from T1 to T2, from T2 to T3, and from T3 to T4. So that's 3 context switches. So the throughput is going to be 4 tasks in, in the length of the tasks plus 3 context switches. So that's going to be the throughput. Now with round robin, depending on how short my time quantum is, I'm going to have more than 3 context switches. So therefore, I'm going to do 4 tasks divided by the length of the total sum of the execution time of the tasks plus whatever number of context switches I do times the time for each one of them. So in essence, I'm running 4 tasks in a longer time period because I'm doing a lot of context switches. Therefore, my throughput has gone down. And that should be expected, right? Because now I'm being fair. It's kind of round robin is being fair. I'm not penalizing short tasks, for example. I'm being fair between short and long tasks. So it's fair, but I'm paying a cost with performance. The throughput is going down, right? Because I'm spending more time on context switches. Okay, so now let's see how performance changes with the length of time quantum. And in particular, let's focus on response time. And let's assume that the context switching overhead is 0. So let's see how it changes the throughput. If the time quantum is too long, then response time will suffer, because if you are a short task, then you're going to wait for, if you remember, the equation was n-1 times q. So if I increase this q, then your wait time is going to increase. And if your wait time increases, then your response time is going to go down. So if you're a short task, you're going to suffer. If it is too short, then throughput suffers, as we discussed, because we're gonna spend a lot of time on context switching, and that's bad. That's gonna make our throughput worse. If the time quantum is infinite, it's the length of it is infinite, then we're gonna actually switch to FCFS, because each task gets to run for as long as it takes, because the length of the time quantum is infinite. So I'm going to finish the T1, and then I'm going to go to T2, and then I'm going to go to T3, and then I'm going to go to T4. So we're going to turn round robin to FCFS if we consider just infinitely large time quantums. It's time quanta. Now, is there any relationship between response time and the length of the time quantum? Meaning that if I increase the time quantum, what's going to happen to my average response time? Is it going to stay the same? Is it going to increase? Is it going to decrease? Or is it going to be a mix? I don't know. If it might increase, it might decrease. The answer will come after this example. So let's consider two tasks, T1 and T2, with different bursts and a time quantum of 10. So with this one, T1, and let's say that the order is T1 and then T2. So T1 is going to run for 10 time quanta, time units, and it's going to be done. Then we're going to switch to T2. So the average response time is going to be 10 plus 11 divided by 2. Now, if I make time quantum shorter, if I decrease the length of time quantum to 5, now I'm going to run T1 for 5, then context switch to T2, and then context switch back to T1. So assuming 0 context switching overhead, the response time, average response time, is going to be T2 now finished at 6, T1 finished at 11, so 11 plus 6. So the response time has decreased. So I decreased the time quantum, the length of the time quantum, as my response time also decreased. Now let's look at another example. Let's say I have 2 with CPU bursts of 1. Let's say time quantum is 10. So it doesn't matter that the time quantum is 10, the length of it, because T1 only has 1 unit of execution time. So it's going to run and finish, and then I'm going to go to T2, and the average response time is going to be 1.5. If I decrease the time quantum to 1, I'm not going to change the outcome. It's going to still be T1 and then T2, and the average response time is not going to change. So in this example, I decreased the length of the time quantum, but the average response time did not change. And in the final example, I'm going to decrease the time quantum from 1 to half. And as you can see, this time T1 finishes at time 1.5. T2 finishes at time 2. So 1.5 plus 2 divided by 2, that's 1.75. Whereas initially it was 1.5. So I decreased the time quantum, the length of the time quantum, and my response time actually increased. So this shows you that they're actually not dependent. So when it comes to average response time and the length of the time quantum, they're not correlated. So there's no direct relationship between the two. Okay, so I'm out of time, so I'm going to stop here. Let me see. Yeah, so we're going to talk a little bit more about round robin and FCFS, and then we'll continue with the rest of the scheduling policies. So thank you for sticking around, attending this lecture. One announcement that I will send an email to the class is that the dean has accepted my request to continue remotely. So I guess I have told ECE students about the reason in an email. So I probably will tell SE students also in an email. It's not wise for me to say the reason here because it's going to be on the on internet. But for a personal reason, a family reason, I requested the university to allow me to continue teaching remotely. And very recently, that request was eventually accepted. At some point, I thought that it won't be, but eventually it got accepted. So after the reading week, we'll continue remotely, at least in terms of teaching. Now, at this point, I have not made any decision on the final exam. So we're going to assume that there will be an in-person final exam. But I think it's too soon to talk about that. So yeah, I've already answered that question. So somebody asked about the final exam. So what I mentioned at the beginning of the term was if the term turns to be a remote term, then we won't have a final exam. But as things stand right now, the university will have in-person final exams. So if we have a final exam, it has to be in person. But let's not talk about it because things could happen. Like we could go back to remote and there would be no final exam. But again, as of now, as things stand, there would be an in-person final exam. But that again might change. I might just remove that option and re-wait. But at this point, I have not made any decision about final exam. We're not gonna have online final exam. That's off table. So any exam with high weight should be properly proctored. So that option is off table. So there is still an option that we won't have a final exam and we will re-wait, but I'm not going to talk about that option yet. So again, to just repeat, all we know at this point is that we're going to have remote lectures and in-person labs, and at this point, in-person final exam. But let's talk about final exam when we get closer to the end of the term. So again, thank you for everybody who supported me. I mean, some of you guys got to know about the reason and the fact that the university hasn't accepted my request yet and reached out. Thank you to you. But eventually it got accepted, so I'm happy. I will send an email to the class and announce the fact that we're going to have remote lectures. Take care, be safe. Talk to you on Thursday. Bye-bye.